Good morning, everyone. My name is John, and we're going to be continuing the advanced Python tutorial. Today, we're going to be moving on from object-oriented programming and just talking about a lot of convenient miscellaneous features that are in the language of Python. All right. To start, Lambda functions. Lambda functions are small anonymous functions defined with this Lambda keyword. They are used to create like one-time throwaway functions that don't need a name. They can take any number of arguments and only have one expression, which is evaluated and returned. This is the syntax for it.
Oh, here it's me.
Oh, sorry. That's good. Thank you. All right, so let's start with an example. First, I'm going to define some synthetic data that I'm going to be using for the rest of the tutorial. Imagine you have some brain image that you want to threshold and keep only pixels above a certain intensity. First, we're going to make this synthetic data. We're going to be using the library NumPy. We create a random seed, and we create some data of a certain shape with integers between 0 and 255. And then we're going to use the Lambda function on this data. There's two functions that I'm going to be using below, which are useful functions. One is numpy.zeroslike. It's used to create a new array with the same shape as some array you already have, which you pass into it, but with all elements set to 0. And the other one is numpy.ndIndex, which returns an iterator, which allows you to iterate over the different indices of a multi-dimensional array. All right, and here's our example with the Lambda function. Here we set a threshold value of 100, and in this line, we define the function. So you're used to functions being defined as multi-line things where there's like the def keyword, and then the name of the function, and then the content. Sorry. But here the Lambda function is being the function is being defined in one line with this Lambda keyword, and the argument here is x, and the contents of the function are here, and it's saying that you should return x if it's above the certain threshold value, otherwise set it to 0. So you've defined the whole function in one line. And then down here you see an example of us using this function. We make a new variable to hold the image after being thresholded. We want it to be the same shape as the old image data, so we use np.zeroslike. Then we iterate through that image using np.ndIndex. And at each spot in the image, we pass in the image data to this threshold function that we defined earlier to get the new thresholded image. Let's see. Let's run this code. So now the threshold of the image contains threshold values, keeping only the intensities above 100. Another useful function for your code is this numpy.vectorize. It takes a function that accepts a scalar input and returns a new function that can handle vector inputs. And it can be often much faster than using for loops. So here is the same example, but using numpy.vectorize. We call np.vectorize on this function. It could be a Lambda function like here or any other function. And this is going to return a new function, which now works on arrays. And then we pass in all the image data, and in one line, it creates the threshold of the image. This is often faster than manually yourself writing the for loop. Right, any questions on that section? Yes, go ahead. Then, sorry? That's a good question. I'm not sure how Python implements the map function, but vectorize is going to, I know that NumPy's vectorize will try to parallelize the code where possible. All right, next section, I'm going to be introducing args and quarks. The arg syntax is a function signature that is used to pass a variable number of non-keyword arguments into a function. Inside the function, args is like a tuple and contains all the passed arguments. A tuple, if you haven't heard that word before, think of it as like a list or a collection of objects. The only rule is it's immutable, which means you can't change you can't change the tuple once it's defined. All right, and here's an example. Here we've defined a function called mean intensity, and it's going to be taking in a series of slices, any number of slices, and then it just iterates over the slices and calculates the sum of that slice and adds it to a total, and the number and the shape of the slice and adds that to the count. So then it divides the count by the total, and that's how it's calculating the mean. And then down here, you can see that we can pass in multiple arguments that are all encapsulated by this single asterisk slices. And in fact, you can throw in as many arguments as you want. Here we're passing in slices from the image data, and it will all be taken under by this star slices argument as a tuple. All right, and next is this quark syntax. And this allows you to pass in any number of named keyword arguments. And this is treated as a dictionary inside of the function instead of as a tuple. All right, here's an example. We're calling this function custom threshold. And apparently it's looking for two different arguments, threshold value and default value, which could be passed in through quarks. And then it's going to be performing a threshold with this default value and threshold value from the quarks. And you can see down here, when we call this custom threshold function, we pass in these named keyword value pairs, threshold value and default value, and that gets put into quarks, which is a dictionary, and then we can get them from the dictionary. By the way, if you haven't seen this get syntax, this is the same as doing quarks threshold value, except for if threshold value is not inside of quarks or any other, if it's not inside the dictionary, then you return 100. So this get is sort of like an if-else statement, where it's saying if threshold value is inside of your dictionary, return the threshold value, otherwise return 100. It's another. But anyways, back to quarks, you can see that you can call this function with threshold value and default value, without threshold value and default value, any number of named arguments, and it all gets put into a dictionary that you can then use inside the function. See if I can zoom out. Oops. All right, and now for our first exercise. You're going to write a function calculate average that accepts any number of positional arguments, which we're going to call data sets, in 3 optional keyword arguments. The first optional argument is average func. This should be a function that computes the average and should default to np.mean. The second and third optional arguments will be scale and offset. If scale and offset are not provided, they should default to 1 and 0. And what the function should do is it should iterate through the positional arguments, which are these data sets, and generate a new list where each entry is the average of that data set, multiplied by the scale factor, and then with the offset added. Next, you're going to write a lambda function called my_mean_f, which uses the sum and length functions to compute the mean. And you can write all of that in this cell here. And then finally, you can test it using this cell here. I'll give you guys 10 minutes to start, and we can add more time if you want. And I also have the solution here, so I can start going through the solution if it gets too difficult. But go ahead. Yes,
Is the most recent ever?
that's a good question. If you check the Slack channel, I think I posted a link to a post that explains how to do it. Yeah, let me know if you can't find it. So this is a tricky one. Do you guys want more time, or would you like me to start going over the solution? All right. So just to reiterate what this function is trying to do. This is the code that's going to test our solution. I created 3 example data sets, which are just lists of numbers. And there's this calculate average function, which we're going to write, and it can take in any number of unnamed arguments that are going to be captured by the args, which are data sets that we're going to iterate over and calculate the average of. And then it has these 3 named arguments. The first is average func. That's the function we're going to use to calculate the average. It could be mean, median, mode, or any function. And then there's going to be these 2 other arguments, the scale and offset, which we apply to the averages. All right, now let me grab the solution. And by the way, if you guys are stuck and just spinning your wheels on one of these things, one of these exercises, all the solutions are already posted on the Jupyter Hub, so you can go and check them after you've spent some time thinking about it by yourself. All right, so here's my solution. There are many solutions you could have to this. Here's the definition, define, calculate average. Here I'm using args to capture however many data sets. And then here, I'm not using quarks. You could use quarks here, but since we know already what the keyword value pair, what keywords we want, I just wrote them out with the defaults on the right-hand side of the equals. And then here I define a list that's going to contain my averages, and I iterate over the data sets that were passed in with this args. And I calculate the average using the average function, and then multiply by the scale and add the offset and append it to this list. And then I return that list. So it's iterating over this data sets that's passed in, and then applying this function to each of them, multiplying by the scale and adding the offset. And then for the second part of the exercise is this lambda function. Here, the input that it's going to take is some data. That's the name of the variable. And here it's taking the sum of the data and dividing by the length of the data to get the average. And then I also have this check here where it says if data, else 0. This if data is shorthand, and that will return true if data is not empty, but will turn false if data is empty. So what this is really saying is if the length of data is 0, return 0. Because otherwise, when you run this line, it will be dividing by 0 if the length of data is 0. That's some shorthand. All right, and then we can test our solution. And here it's calculated the averages for each of the data sets, multiplied by the scale with the offset added. This first one is using this median, and these second 2, one of them is using numpy's mean, and the other one's using the mean function that we wrote. So they should be the same. All right, that was a lot. Any questions on these first 2 sections? Right. All right, moving on to generators and list comprehension. A generator is a special type of iterator that lets you iterate over a large sequence of values lazily, one at a time. They're defined very similarly to a function, but instead of having a return statement, they have a yield statement. So we have this 3D synthetic data that I defined at the top. And imagine you want to iterate over one of the axes of this data. So iterate over slices of the brain. You can make this generator here that will yield them one step at a time. So this generator takes in the 3D data. It iterates over the first axis for this example here. And then instead of like appending to a list or putting it in an array or returning it, we have this yield statement. And this yield is telling it that each time you call this function, you're going to return this. And then the next time you call it, it will go through the for loop again and return this again. I'll show you. I'll show you what this example looks like. So, for example, here, this is a for loop where you're iterating over the results of the generator. So this is the generator on the right, and this is the result of the yield statement on the left. So as you go through this for loop, it's as if you're going through this function, getting the results of the yield, and then you just keep going through the for loop in here. So, you can also use the next function to manually iterate through the values generated by a generator. So here we're calling this generate slices, and the first slice you can get by calling next on the results of this function, and that will get you the first yield that this for loop hits. And then if you keep calling next, it will get the next yield and the next yield after that from the for loop inside of the generator. There's also a syntax called generator expressions. I don't use these that often, but they're there. It looks like this. Here, let me try to think about what exactly this is. It's calling custom threshold on image slice for each image slice in the image data. And so you get, so this custom threshold is just a function, and it's being called within a for loop. So it's a way to write a generator within one line. So this is similar to the results of the generator. You can call next on it, and each time you call next, it'll get the next threshold in slice. And then finally, this it doesn't have to do with generators, but it's got a similar syntax to generator expressions. This is list comprehension. And I found this to be very useful for simplifying code and making it a little shorter. A list comprehension is a one-liner that creates a new list by applying some expression to each item on an existing iterable. The basic syntax is similar to generator expressions, but using square brackets. So here we have our image data, which is this three-dimensional array, and we're iterating over it in this for loop and getting an image slice each step of the for loop. And then we're calling this function, we have custom threshold on the image slice. But there could be inside of a list comprehension, you could be doing anything that's within one line on this left-hand side. And what this does is it creates a list where inside that list, custom threshold has been called on each image slice from the image data. So it's a one-line way of creating a list. And so since it's a list, we're no longer calling next. We're just looking at the first element of the list. All right, so for this exercise, we're going to be looking at this function we generated earlier. I'll just bring it down for ease. So we have this function calculate average, which has 4 lines in it. There's a list of averages, and then we iterate over the input data sets and append to this list and then return it. We can now simplify this. The first step in this exercise is to create a new function called calculate average 2. And this should be a generator that does the same thing as calculate average, but instead it's using yield. And this will only be 2 lines long. And then you can rewrite calculate average using list comprehension. It will return the same thing as this function, but it should only be the contents of the function should only be 1 line long. So I'm going to give you 5 to 10 minutes. We'll see how it goes to try and rewrite this function that we wrote earlier, but instead as a generator and then also using list comprehension. And also let me know if you have any questions. All right, I'm going to start typing out the solutions. If you've already finished it, that's great. If not, that's great too. You can watch, now that you've had a chance to look at the problem, you can watch to see how I would do it. There are many ways of doing this. So first off, we're going to write out calculate average 2. This is going to be a generator. It's going to have the same start as the normal function. The difference is we don't have to define this list of averages, because instead in this for loop, we're just going to yield, what we were appending to the list. So in the previous function, we had this list, and in the for loop, we were appending our results to it. And in this new function, each time in each iteration of the for loop, we're going to yield our results. And then for calculate average 3, this is the one using list comprehension, which ends up having the fewest number of lines. For list comprehension, first, we're going to put the value at what we're trying, the contents of the for loop. And then we're going to say for data set in data sets. And that's what that syntax looks like. So hopefully all of these functions do similar things if I haven't made a mistake, which is possible. And then we'll test some with this code. So this first print statement comes from using the calculate average function, just the normal one, and it generates a list. And then this calculate average 2 is a generator, which yields the similar results. But one of the differences between generators and functions is the results are not all calculated at once and returned at once. Instead, we're calling next on what calculate average 2 returned. And each time we call next, we get the next result. So this can be useful if you have a more complicated function, which maybe the results take up a lot of memory and you only want to process one thing that comes from the function at a time. Instead, you can use a generator, and then instead of having all of your results calculated at once, you're hitting these yields and you're calculating the results one at a time. All right, and finally, we check that the list comprehension implementation gets the same results as the normal implementation. All right, go ahead. That's a good question. I don't think there is a difference in performance. Ariel, do you have anything to add on that? Is list comprehension faster or slower than using a for loop?
No.
Good question. Right. Oh, go ahead.
Quickly look into efficiency. Is there some way to do that?
Yeah, actually, later in this tutorial, we can skip ahead to that because these are all actually pretty independent of each other. But I have a section on timing. But yeah.
Yeah, my question is about the generators. So it seems like you can just move on to the next field, so it's more computationally efficient or doesn't use it effective RAM. I guess have you ever used it only once? Or like I guess I'm kind of thinking about like what is the generator just the function that's stored in its current state, or
Yeah, it's a function that's stored in its current state, and I believe you can use it only once. Is that true? Yeah. Yep.
so like if you're ever doing anything with like random generation, you want to make sure that always have your seed, or else it could the generator could be something different the second time you use it.
Yes.
Right?
Yeah.
Instances where like we wouldn't want to use the generator.
Yes. Since, as you said, it's storing the state of the function. If the state of the function, like all the variables that are in the function, are using up a lot of memory, and the thing you're returning actually isn't using that much memory, then it's probably not useful. Also, just in terms of syntax, if performance isn't an issue, it is a little weird because it returns like a generator object, and then you handle that differently than list, like you're using the next function a lot, or you can cast it to a list. I don't know. The code just looks different with a generator, so I would only use it if it made sense to use it. If the things you're returning are like
John,
really big.
can you repeat the questions?
Oh, sorry. So one of the questions was, are there ways of monitoring the performance or of seeing the performance? Because we've talked about performance a little bit and about which techniques are faster or slower. And I said that we're going to skip ahead to the decorator section because I have a little bit about how to monitor performance in there. And I should also mention, so in the decorator section, it's just going to be a timer thing where we're looking at the timing of these different functions. But if you want to worry about memory, I think there's a library called Memory Profiler on PyPI, that library can be used for profiling memory. And then the most recent question was on when to use generators, when to use them and when not to use them. And I would only use generators when you're calculating something that's memory intensive and you only want that one at a time. All right. How are people feeling about the material so far? All right. Awesome. All right, I'm going to skip past the error section for now and go to decorators. So a decorator is a higher order function that takes a function and extends the behavior of that function without explicitly modifying the code. Decorators are often used to encapsulate common functionality that can be applied to multiple functions or methods. Here's an example. So we have this function called myDecorator, which is going to take in a function. And then inside of that, we're defining this function we're calling wrapper. And that function inside of a function is then calling what you passed into myDecorator. But you can do stuff before and after the function that it's calling. So that is what defining a decorator looks like. And it's going to take a while to get used to the syntax because it's very confusing. But once you get used to it, it's very useful. And this is what it looks like in practice. You have this little @ sign and the name of your decorator, and you put it outside of a function. So this function, say hello, prints hello, and this decorator will wrap it in these two print statements. So when we actually call say hello, the decorator has done something before and something after the actual function call. This @myDecorator thing is what's called syntactic sugar for this statement, say hello equals myDecorator with say hello passed in. So this format here, you could get rid of the @ here and instead do this. And so you can sort of see what's happening here. There's this function myDecorator, and you're passing in a function, and it itself returns a function. So the decorators are functions where you pass in a function and they return a function that is modified. All right, so the reason this has to do with performance is because in this example, I'm creating a timer decorator. So we're going to import this library called time, which can be useful for measuring performance. And then inside of our timer decorator, before we call the function, we're going to get the start time. And after the function, we're going to get the end time. And then we're going to print the difference between the end and start time to see how long the function actually took to compute. And then down here, we have the two functions from the first example. One is applying the threshold function to the image data using NP vectorize. And in the other one, we're applying the threshold function to the image data by just using a normal for loop. And in both cases, we're passing these functions into our timer decorator so that we will get the time it takes to execute each of them. All right, and you can see here that it corresponds to what I said earlier. The loop took 0.18 seconds to execute, whereas the vectorized version took 5 seconds to execute. And this is because the NumPy library is probably doing is doing a lot of optimizations inside of this and parallelizations where it can. All right, and finally, it's useful to know that the decorator itself can have arguments. And then in that case, the syntax gets even weirder because what you have is this outside decorator function, which has the argument. And inside of that, it's returning this a decorator function where the argument is applied. And that decorator function is taking in the function you want to decorate and wrapping it and returning a new function with the wrapper around it. So again, the decorators get a little confusing, but they can actually simplify code a lot if you have a lot of repeated code. So it's okay if you're confused about the syntax now. I just wanted to show it. All right, and here's an example. You can also put multiple decorators on one function. So here we have a function that's just one line with the vectorized, and then we're putting a logger decorator on it, which tells you that you're calling the function, and a timer decorator. And so now this one line function has all this information about what happened in the function from the decorator. So you can hopefully see how this can simplify repeated code. All right, and we have an exercise for this for decorators. In this exercise, you're going to be creating a greeting system that can greet people in different styles, and you're going to be using a decorator to do that. So in the code I've already given you, there's this function greet, which returns a greeting, hello, and then the name. And what you want to do is write a decorator, 3 different decorators, polite greeting, shouting greeting, and question greeting. And what they're going to do is decorate the greet function. And the polite greeting is going to add please to the beginning and thank you to the end. The shouting greeting will make the entire greeting uppercase, and the question greeting will add how are you today to the end of the greeting. So for this exercise, you're going to be implementing these 3 decorators. Go ahead.
Is the logger decorator kind of a fancy way of just doing statements throughout your code, telling you where you are and what function that was run?
Yeah, so the question was, is the logger decorator a fancy way of doing print statements throughout your code? That's a good question. This logger decorator, I think, is mostly being used for an example. So I don't think you'd have a decorator that, I don't know if you would actually be able to use this actual decorator, this decorator that I've written in code and have it be useful. That is what it's doing. Yeah, like a fancy way of doing a print statement. But you could imagine maybe in your code that there's actual functionality in here instead of just a print statement. Does that make sense? For example, you could modify the arguments as they're coming in. So in this, there's the args and quarks. You could, maybe it's a function that takes in a path to a file, but inside the function, you're using the actual, like, the function wants numpy data, but the function can ask for both a file or the numpy data. Then inside the decorator, you could have a little if statement that says, if this is a string, then load the file using numpy. And then you could put that on any function you want that has that situation. Does that make sense? All right, thanks. All right, I'm going to give 5 minutes or so to do this exercise. All right, so in the interest of time, I'm going to cut this a little short and try to go over the answers. All right, so here's the solution. The first polite greeting wrapper, you are adding please before the results of the function and thank you after the results of the function. And so when you call the function with a certain name, the string gets prepended and appended. For the shouting greeting wrapper, the syntax is like this, and inside I'm calling this dot upper function. So the result of this function name is a string, and then you call dot upper and all of the alphabetic characters become uppercase. And then finally in the question greeting, I've taken the results of the function and added how are you today to the end of it. All right, so in the interest of time, I think I'm going to skip over duck typing, but go ahead after class if you feel like this might be useful. There's a few sections we're skipping over with some exercises and solutions. Go ahead and go for it after class if you think it's useful. I do want to spend some time looking at doc strings. So doc strings are a way of documenting your code. They're an essential part of writing maintainable and understandable code. It's basically a convention for how you describe the functions you've written. So a doc string is a string literal that occurs as a first statement in a module, function, class, or method definition. They're a great way to provide documentation. And here's a simple example. If you haven't seen this triple quotation marks quote syntax before, it's the same as doing a multi-line comment. So if you have a comment that is so big that it takes up more than one line, what you can do is just have 3 quotations. And then inside of those quotations, everything inside the quotation is a comment. So doc strings typically use this syntax for doing a comment. Here we have a function add vectors. It takes in 2 arguments, v1 and v2. And then inside it's using list comprehension with a zip function to just add up the elements inside of these vectors. What's happening inside isn't important though. You don't actually need to know because we've written a helpful doc string, which explains what the function is doing. So if you're ever writing a function that can be, where the contents might be complicated, or even if the contents are simple, if you want someone else to be able to use it, it's good to write these doc strings to tell people how to use the function. So there's this standard PEP 257, PEP 257, which provides guidelines on the standard way to do doc strings. They typically look something like this. The first line is a description of what's happening in the function. And if the function is small enough, maybe the description is all you need, or if it's straightforward enough. But a lot of the times you're also going to want this parameter section, which I think is really useful. And that describes what parameters the function accepts. It usually has their type, a description. And if it's a keyword value pair, you can also say what the default value is, like that. And so this is really useful because if someone else is walking up to a function they don't know, and they're looking at this list of arguments, they can read through the documentation here and see like, this is what I'm supposed to pass into this function. And then you provide what this function returns in the doc string. So I think for writing good code that's easy to maintain, for your future self to understand what a function does, for other people to understand what a function does, it's good practice to write these doc strings. Yes.
At the beginning of defining assembly, is there a way to like make sure that each path is only another string? Or would you have to like code that into an actual function for it to?
That's a great question. Typically, you're going to want to code that into the actual function. Something like if image path is a string, or if type of image path equals string is one way to do it, and then write a type error otherwise. There is another way of doing it. I mentioned somewhere in these docs. Oh, here it is. This is a typing library that's not often used, but I like it. I like when I see people using it. And this allows you to put in your function explicitly what type. So this is the add vectors function we were talking about, and here v1 is said to be a list of floats. and then v2 is a list of floats. And then it's saying here that it's returning list of floats. And so this is the syntax for using that library. And if someone then passes in something that's not a list of floats with this syntax, it will throw an error.
We kind of do also like the parameters are in front of the arrow and then the returns are after the arrow.
Yes. Yep.
Does it need to be a list type or can it be list like that? All right.
That's a great question. I don't use this library that often. I kind of want to switch to using it more often. I think it's a nice idea, but I haven't used it often enough to know. I'm sure they have a way of doing it list like. So yeah.
Yeah, this is a weird kind of new feature of the language that's not actually, it doesn't really affect runtime behavior yet, but maybe in Python.
Yeah, right now I think it will just like, it will throw like red squiggly lines and things like that if it sees it being used improperly. But yeah, this gets into type checking, which we talked about yesterday, which is good practice. All right, any more questions on all of the content today? All right, thank you.